Tonight's movie is on gases and stoichiometry. A little bit of recap from what we already recall from stoichiometry before we get into the gases piece. When we're doing stoichiometry, it's basically a write a balanced chemical equation. We're going to do one factor or conversion to get something from a mass typically or concentration and volume into moles. We then apply a mole ratio. And then we have some other conversion, whether it's in with volume or concentration or molar mass, to get it into whatever desired quantity we want. So the factor method typically is a balanced reaction, then 3 conversion factors. Now we have the capability of including gases, not just dealing with solids and solutions, because we've got the ideal gas law to get us to moles. We're going to move on to the next slide in 3, 2, 1. You have a handout that looks like this in your notebook somewhere, and what you want to do is you want to find that slide or that handout. The pieces that you see here you should already have on your page. You already should have some pieces added in with respect to molar mass and concentrations and volumes and things like this. Now I'm going to focus in on this one right here. PV equals nRT. That's the tool that we're going to use to get into stoichiometry, which means if we have pressure, volume, and temperature, we can use it with R to get to moles. Once we've got the number of moles of something, we can apply a mole ratio. That gets us moles of something else in a balanced chemical equation. And then, again, using R, we can get one of pressure, volume, or temperature, as long as we've got the other two. Most of the time, what we're working out is a volume of a product gas or volume of a reactant gas that's needed. That's usually what we're doing because the pressure and temperature conditions are typically the same as the reactants or the starting materials that we're using. So that's what we're likely to do. So on that handout, please add in P, V, T, and R, and add in any other of those reactions that you might not have listed on your original page. And we're going to move on in 3, 2, 1. Saltpeter, which is a chemical with a symbol of, okay, green should show up nicely, KNO3, and it reacts to make potassium oxide plus nitrogen plus oxygen. That's a gas, that's a gas, that's a solid because it's ionic, and that's a solid because it's ionic. Saltpeter decomposes according to this reaction. If I happen to have a 2 gram sample of saltpeter, what volume of gas is going to be produced at 385 degrees Celsius and a pressure of 2.35 atmospheres. Saltpeter is one of the chemicals that goes into gunpowder mixed with carbon and some sulfur, and so this provides the oxygen necessary for the rest of the reaction. We're going to balance this, and we find that we get 4 potassium nitrates, makes 2 potassium oxides, 2 nitrogen, and 5 oxygens. We're going to write down our given information, and so we've got a mass of KNO3 equal to 2.00 grams. At this point in time, I trust that you can work out the molar masses without having to review this. Okay, we're going to look at 1 potassium, 1 nitrogen, and 3 oxygen. You look up their molar mass or atomic masses on the periodic table, multiply the oxygen by 3, add the rest of them up. You will get 101.11 grams per mole. Other information is that we have a temperature equal to 385 degrees Celsius. We know we've got to add 273.15 to give us 658.15 Kelvin. The last piece of information given is that we have pressure equal to 2.35 atmospheres. Atmospheres is one of the units that works well with the ideal gas constant, so we probably don't need to convert that. Now we're on to the stoichiometry piece. We're going to start with that 2.00 grams of KNO3. The molar mass lets us say that for every 101.11 grams of KNO3, I'm going to have 1 mole of KNO3. The grams of KNO3 cancel, and now I have everything in moles. Missed the L. Let's change it to black. Okay, do. My mole ratio then is for every 4 mole KNO3. Now notice the question carefully. It says what volume of gas is produced. What volume of gas? The 2 moles of K2O do not count. However, the moles of nitrogen count, the mole of oxygen count, which means we add the 2 plus the 5 and we get 7 mole of gas. This is a different question. It's asking how much gas is produced, not how much oxygen, not how much nitrogen. It's asking what volume of gas is produced. So now it only matters which gas it is. Dalton's law of partial pressure says the pressures will simply add, so I may as well find out how many moles of gas I've got, add them all up, and do the last conversion by itself. This allows me to cancel the moles of the KNO3. My calculation will now be 2 times 1 times 7 divided by the 101.11, again divided by 4. And this, when calculated out fully, will give me 0.03461 mole of gas. Now to make sure I don't run out of space, I've got an extra slide ready that's just blank. The pieces I'm going to need to bring forward onto the next slide are going to be the temperature, the pressure, the number of moles of gas, and I'm going to look up R, and we're going to do all of that on the next slide so we can see it really clearly. So we're going to move on to the next slide in 3, 2, 1, now. The base formula, PV equals nRT. Because we are going to want volume, we're going to divide by P. And that means V equals nRT over P. Now we're going to start our substitutions. From the other page, we have N equal to 0.03461 mole times. Now, because we've got to pay attention to our pressure units, we said that the pressure for this was 2.35 atmospheres. So when I go to put in R, I need to put in the version that has atmospheres in it. That's 0.08206 atmospheres, liters per mole Kelvin. And then I'll multiply lastly by the temperature. The temperature we worked out to be 658.15 Kelvin. We check to make sure that our units cancel, so the atmospheres in the denominator and the atmospheres in the numerator cancel. moles and inverse moles, Kelvin and Kelvin. I'm left with liters, which is the volume unit that I want, which is fantastic. So it's just a matter of multiplying the three numbers in the numerator, dividing by the 2.35, and I will be left with 0.796 liters. And because most of our values in the question were given to three significant figures, that's the detail we need to show. Moving on to the next slide in 3, 2, 1. Last question, again I've got a second slide just in case I need more room. If 1.33 grams of sodium reacts with excess hydrochloric acid in a single displacement reaction, what volume of gas is produced at 20 degrees Celsius and 755 torr? All right, let's get down our given information. We've got a mass of sodium of 1.33 grams. Since that's the only mass I've got, I'm pretty confident I'll need its atomic mass. And that's 22.99 grams per mole. I have a temperature equal to 20.0 degrees Celsius, which as usual, I'm going to add the 273.15 to get 293.15 Kelvin. And the last piece of information I've got is a pressure equal to 755 torr. And torr is not one of the units that I can work with for the ideal gas constant, so I know I'm going to convert this into kilopascals or atmospheres. I tend to like to work in atmospheres just because I'm just used to it. So I'm going to multiply by 760 torr in the denominator, because the numerator is exactly 1 atmosphere. So when I cancel, torr units cancel. When I do my calculation, I know I'm going to get a value just a little bit below 1, because 755 is just under 760, and my value is 0.9934 atmospheres. So those temperature and pressure values I'm going to use in the ideal gas law, and the mass and atomic mass I will end up using when we do our stoichiometry piece. This is going to require skills from previous in the unit. We are told it's a single displacement reaction. We're told that the reactants are sodium and hydrochloric acid. So hopefully you can remember or look up. Sodium is Na. It's a solid normally, and it is not diatomic. Hydrochloric acid, the hydro means there's no oxygen attached, so it's HCl. That's aqueous. It's a single displacement reaction, which means that sodium, because it'll gain a plus charge, is going to go in and replace the hydrogen because it has a plus charge. So those two are going to swap positions. I'm going to get hydrogen coming out. Hydrogen is one of the elements that comes in pairs, so it's going to be H2, and it is the gas at room temperature. And the other product is NaCl. Sodium's +1, chlorine is -1, so the crossover rule just gives one of each. And the hydrochloric acid was aqueous, and the sodium chloride is aqueous as well. That's the skeleton reaction. Balancing requires that I put a 2, a bolder color there, a 2 in front of the HCl, a 1 in front of the hydrogen, a 2 in front of the sodium chloride, use up the chlorine, and that means I need 2 sodium. There's my balanced chemical reaction. Now I'm going to be working on the mole idea to get from moles of sodium to, grams of sodium to moles of sodium, and moles of sodium to the number of moles of gas produced, which is the hydrogen. That means I start with the 1.33 grams of sodium. The molar mass piece is 22.99 grams of sodium for 1 mole of sodium. That lets me cancel grams of sodium. And then I'm going to multiply by the mole ratio. For every 2 mole of Na, I get 1 mole of H2. That lets me cancel the moles of Na. And when I go through this process, notice I keep the gas calculation separate. This one is usually much easier to do in steps. So it's 1.33 times the ones, divide by 22.99 and divide by 2. And when I complete this calculation, I should get 0.02893, which I know is more significant than I need to carry, but because I need to have minimize the rounding errors, I'm going to carry extras for now, and I will then round at the end. That's moles of H2 gas. So I'm going to carry on to the next page, the moles of H2 gas, the pressure, and the temperature. I'm going to move on to the next slide in 3, 2, 1. Like the last time, we're asked to get our volume, which is going to be nRT over P. You'll find that's a pretty common combination. The number of moles we said was 0.02893 mole. Again, I chose to work in atmospheres, so it's 0.08206 atmospheres, liters per mole Kelvin. The temperature this time around was 293.15 Kelvin. And the pressure this time around was 0.9934 atmospheres. Check to make sure everything cancels. Moles and inverse moles, atmospheres and atmospheres, Kelvin and Kelvin. Leaves us with liters, which is what we expect. And when we do all the calculations, and we have to round this to 3 significant figures because of the mass of the sodium, we get 0.700 liters of H2 gas. Both of these examples were producing gas. I could have done an example where we started with pressure, temperature, volume, and work out number of moles of a gas, and then we'd use a mole ratio, and then work something else out with a conclusion. So these two just happen to end with this calculation, but it could have started differently. Thanks for watching.